Hello guys, how's it going? Mike coming back at you here with another video on discrete mathematics. In the previous video, we looked at more truth tables. We saw some truth tables that involved the conditional operator, and then we also saw and we verified the logical equivalent of a conditional statement. Just as a quick recap, the logical equivalent of P implies Q is not P or Q. So this video is going to be a continuation of the video prior to that. We're going to kick it off by talking about three statements that are related to a given conditional statement. Each of these three statements has a name. The name you may have heard of from previous math classes. The inverse, the converse, and the contrapositive. So if you're given a conditional statement, P implies Q, the converse is given by Q implies P. So what you're doing here is you're switching the places of P and Q. So I like to think of converse as switch. To just give you a quick sample of this, suppose my sentence was, if the sky is blue, then the grass is green. The converse of that sentence would be, if the grass is green, then the sky is blue. Just switching the places of the pieces making up that conditional statement or that sentence. The inverse of P implies Q is going to be not P implies not Q. So you're going to take the not of each of your pieces and then do the implication or the conditional in the same corresponding order. So the inverse of my sentence, if the sky is blue, then the grass is green, would be, if the sky is not blue, then the grass is not green. The third one is called the contrapositive, and the contrapositive is sort of doing the inverse and the converse in one. The order in which you do those things does not matter because it gets you to the same end result, but the point is you're going to take the not of P and Q on their own, and then you're going to take those pieces and then you're going to switch them. So the contrapositive is not Q implies not P. The contrapositive of my sentence, if the sky is blue, then the grass is green. The contrapositive of that would be, if the grass is not green, then the sky is not blue. Now the big question is, how do these four things relate to each other? The given conditional, its inverse, its converse, and its contrapositive. Well, the given conditional statement and its contrapositive are logically equivalent to each other. And then the inverse of the conditional and the converse of the conditional are logically equivalent to each other. However, going between those two pairs, there's nothing logically equivalent to each other. So the converse is not logically equivalent to the conditional or the contrapositive, and same goes with the inverse. So two separate pairs of things that are logically equivalent to each other, but not between those two pairs. And in the next video, we're going to verify one of these pairs being logically equivalent. There's one more conditional, there's one more operator that we want to talk about and add into our list of logical operators. This one's called the biconditional. If you have statements P and Q, then the biconditional is read as P if and only if Q. In mathematics textbooks, you'll commonly see it shortened to PIFF-Q. That IFF stands for if and only if. And because mathematicians can't be happy with just writing 3 letters instead of 4 short words, we have to symbolize it further. We do that by P and then a double facing arrow, both left and right, and then Q. So P if and only if Q, P I F F Q, and then P double facing arrow Q. All 3 ways of saying the same thing. The truth table for the biconditional. The biconditional is only true when P and Q have the same truth value. If P and Q are both true, then P if and only if Q is true. If P and Q are both false, then the biconditional is also true. If P and Q do not have the same truth value, then the biconditional is false. And we can show, using truth tables, that the logical equivalent to P if and only if Q is P implies Q and Q implies P. So we have to show that those conditional statements on their own are true, and then take the conjunction of them, and then you get your logical equivalent. And this is a very basic logical equivalence, but it's used very, very heavily in the world of mathematics. If you go on to take higher level math classes, you'll see that when you have to prove a biconditional theorem or a biconditional mathematical fact, something of the form P if and only if Q, you'll see when you learn how to formally prove these things that you are using this guy right here. You're going to prove 2 separate conditional statements within one. But last thing I want to talk about for this video is a phrase that we use in mathematics, not so much in everyday talk, but this phrase does show up from time to time in mathematics and mathematical textbooks. So I just want to get into that phrase, what it's actually saying in terms of logic. But before we get to the entire phrase, we introduce the pieces of it and what those pieces are saying. So if we have statements P and S, or P and Q, whatever, to say P is a sufficient condition for S means if P, then S. Or in terms of the symbology, P implies S. To say that P is a necessary condition for S means if not P, then not S. Or not P implies not S. Well, we mentioned in this video that a conditional statement and its contrapositive are logically equivalent. So if I take the contrapositive of not P implies not S, then that thing is also true. And the logical equivalent of not P implies not S is S implies P. So we have sufficient condition, meaning P implies S. P is a necessary condition for S, means S implies P. If we take the conjunction of those, we get P implies S and S implies P, which is the biconditional P if and only if S. And now we come to that famous phrase that we see in some textbooks. To say P is a necessary and sufficient condition for S means P if and only if S. Now there was a righto in my notes. I had written if not S, then not P. That is a righto. It should be if not P, then not S. So if you're printing off the notes, be sure to make that change. So this was just a bit of an introduction into inverses, converses, and contrapositives of conditional statements, how they relate to each other, and then the biconditional operator. Its truth values, its truth table, its logical equivalence, and then just a brief little side venture into this fairly common mathematical phrase, or this fairly common phrase that you see in math textbooks. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.